The average value of a function is another illustration of the integration way of life, but it's also a very, very useful thing. It's one of the primary steps in any kind of statistical analysis. So you have a function, and you've got this task of assigning a single number to it. I mean, when you have the average of a list of numbers, 8 plus 6 plus 7 plus 5 plus 3 plus 0 plus 9, then divided by 7, and that gives you the average of those numbers. And that's getting a single number out of some set of numbers. So here we have a lot of numbers. We get all the values of this function f, and it's really often the case that you need the average of those. And that doesn't make any sense. There are an infinite number of them, but we practice the integration way of life, which means we do the following. We're going to subdivide this region where the function is defined. So there are the subdivisions, and it's okay in this case for the values to be negative as well. So keep that in mind. And if we have n subdivisions, then delta x, the size of the interval in each one, is a fraction. The top of the fraction is the length of the interval, b minus a, and the bottom is n, because you've just divided it into n even pieces. In more advanced things, you don't have to subdivide it easily, but this will get you through understanding what's going on. And then now we've got a finite bunch of things, and we can sample in each interval. Some of the samples are going to be negative here, so these are the samples. We'll call those f sub 1 through f sub n. And now we have a finite list of numbers, and samples might just be 8 plus 6 plus 7 plus 5, 3, 0, 9. And so this is a finite number, and we can take the average of this set of data. This is just a few things. It might be a million, but we'll still take the average. So that approximate average based on the samples it's a fraction. The bottom is n, because when you take an average, you add up everything and divide by n. And then the top is the sum of the samples. That's what happens when you integrate. Now, this doesn't look like an integral at all. So this is the clever part of the integration way of life. And here's what's going to happen. It goes back to this little piece of algebra right here. Each of these samples is divided by n. So I'm going to rewrite this. This is our complicated algebra for the day. Instead of having a fraction with the sum on top and n on the bottom, I'm just going to distribute out that n. So now we've changed the way it looks, the presentation, but we haven't changed the value, so that's good. And now if we compare this pink with this pink, there's an n on the bottom in each of those, and that's going to be the key to making this into an integral. So here's what happens. Based on that calculation of delta x, 1 over n is 1 over b minus a times delta x. And all I've done is taken this and divided both sides by b minus a. So now down here I've got 1 over n, and up here I've got 1 over n. And so the sum becomes 1 over b minus a times f sub 1 times delta x. And you keep doing that in that same pattern. So 1 over b minus a times f sub n times delta x. So we've just done a little bit of algebra, really very, very little algebra. And now we've got this expression, and that is an integral. That we recognize as being one of the sums for the integral, not of f of x, the function that we're originally given, but of a different function, 1 over b minus a times f of x. And so this is now, we've subdivided, we used the same subdivision, we've sampled, but now the sample has to be divided by b minus a and taken the sum, and we know what the limit's going to be. So in the limit, what you get is the integral from a to b over the whole interval, and then this factor, the fraction, 1 on top, b minus a on the bottom, f of x dx. And so this is the average value of f over the interval. Probably takes longer to write it than it does to do it. And so that's the solution. That's not what it says in the books. So what's gone on here? What's gone on here is that I have gone through the process of finding out how to turn this problem into an integration problem. And I found out that we were integrating a modified function f, and the modification in this case was to multiply by this little fraction. And so what's in the books is they say, hey, a constant comes out of the integral. And so the books all say the average value is the following. They take that fraction, 1 over b minus a, and then they take the integral from a to b of f of x dx. So this is what's in the books. These are absolutely equal, same value, same number, but different presentations. And the book presentation, this is in all the books for the past 2 centuries, is wrong. It happens to be, by coincidence, equal. Now, the problem is that in other problems, what you're going to see is not something that gives you a modification by a constant, but something that gives you a modification by another function. And if that's the case and the other function isn't constant, this final step here, you can't make it. And so I prefer to keep this in the form of all the other steps that you might be making, or I'm sorry, all the other conclusions that you might be making. This one, by lucky coincidence, has a constant. But the general case of doing this integration is that what you're going to find is that you're going to be taking the integral from a to b, that's the interval that you're over, and instead of the constant 1 over b minus a, there's going to be a function which is traditionally called k, so k of x, f of x dx. Now, if k is not constant, you're not going to be able to take it across the integral. The b minus a you can, because that's a constant. But so this is the more general solution to lots of different integration problems. In my notes, there's a list of all of these. These come up really often. And so the first example of doing it and illustrating the integration way of life is this average value. And it's pretty useful, and it generalizes quite nicely.